The first mode of CORDIC algorithm operation is a rotational mode. In this, the coordinate components of the vector and the angle of rotation are given by the coordinate components of the original vector after the rotation through the given angle are computed. Within this, the accumulator angle is initialized by a desired set of angle rotation. The decision of rotation is based on the sine of the residual angle of the angle accumulator. Therefore, I need two variables with respect to the signal and one variable with respect to the angle. So, the two variables with respect to input signal, I will be assuming it to be xi plus 1 and yi plus 1. And the angle, one variable with respect to the angle, I need to assume it to be zi plus 1. Therefore, I can write this to be xi plus 1 is equals to xi minus yi into d power minus I into 2 power minus I. Similarly, yi plus 1 is equals to yi plus xi into di into 2 power minus I, and 1 with respect to fixed angle of rotation zi plus 1, which will be zi minus di into tan inverse of 2 power minus I. Since the input angle is expressed with respect to binary arc tangents, the accumulated angle is necessary to be di equals to, this condition it must get satisfied, minus 1 if the value of zi is less than 0, and it should be plus 1 otherwise. Make a point here, this zi with respect to the angle of rotation, fixed angle of rotation. Then finally we can express this to the form xn is equals to an into x0 into cos z0 minus y0 into sin z0. Similarly, yn is equals to an into y0 into cos z0 minus x0 into sin z0, and the value of z0 will be, zn will be 0, and an, the most common factor with respect to signal in the mathematical expression, will be pi into 1 plus 2 power minus I. So these are the binary arc tangent values. You can observe here, as said earlier, theta is equals to tan inverse of 2 power minus I. In place of I, the value of I will be ranging from 0 to infinity. So the values are being mentioned with 0, minus 1, minus 2, minus 3, minus 4, and so on. Those computed values which are then converted into binary, these binary values are then stored in the lookup tables. It's only because of these values we are going to generate the signal with respect to the fixed angle that we will be giving, either with respect to sine waveform or with respect to cos waveform. Now coming to the vectoring mode, the magnitude and the angular movement of the original vector are computed here. It works by seeking to minimize the y component of the residual vector at each rotation. Also, the sign of the residual y component is used for determining the direction that is to be rotated further. Much similar to your rotational mode which I have seen in the earlier case, even here we need to have two variables with respect to the input signal and one variable with respect to angle. So the mathematical expression with respect to vectoring mode will be much similar to your rotational mode, which is xi plus 1 is equals to xi minus yi into d power minus I into 2 power minus I. Similarly, yi plus 1 is equals to yi plus xi into d power I into 2 power minus I. Much similar with respect to angle, zi plus 1 is equals to zi minus d power I into tan inverse of 2 power minus I. Since the rotation is initiated to 0 and accumulator contains the transverse angle of the previous end, thereby we can consider here di is equals to minus 1 if yi is to be 0. You need to make a note here, earlier we had placed a limitation with respect to the fixed angle. Now we are placing a limitation with respect to the another input signal, and it will be null otherwise. Thereby the final expression will come around xn is equals to n into square root of x naught plus y naught square and yn is equals to 0, followed by your zn value will be z naught plus tan inverse of x and y. Finally, the same expression an is equals to phi into square root of 1 plus 2 power minus 2y. If you could observe in the earlier case, here the value would remain minus I, but now it is remained with respect to minus 2 power I, and this is with respect to vectoring mode, and this would be with respect to rotational mode. Finally, this is my CORDIC representation with respect to variables xi, yi followed by zi. By setting this x value input to 1 by a power n, the output of the CORDIC rotator is scaled by rotator again. If the obtained gain is not acceptable, a single multiply is performed as a reciprocal of the gain constant placed before the CORDIC rotator, and this will yield to the unscaled results. And just by performing this shifting and accumulating operation, the output signal is generated. Let's see how we design it in Verilog.